Welcome to the part 3 of Laplace transforms. It is completely dedicated only to one small concept called as first shifting theorem. It is also called as a S shifting theorem. Why it is called as a S shifting theorem, you will come to know when you see the statement of this one. The statement of the theorem is like this: if Laplace transform of f of t is some function of s. Now you need to understand what is said here, that is, if the function f of t has the Laplace transform f of s, then the Laplace transform of this same f of t, whatever f of t is there, when it is multiplied with exponential function with a as the constant here, it's a product of two functions of which one of the function is that one whose Laplace transform we already know. Now this theorem helps us in telling what will be the Laplace transform for the product if one function's Laplace is known. This says very simply, whatever function you have, in that same function instead of s, you substitute s minus a. You substitute s minus a. Now let us first understand the statement. Without understanding the statement, it is best to go for the proof. Okay, if you know the proof and you don't know what that statement says, it's of no use. Okay, let me say, if we know that, okay, I am directly using it. We know that Laplace transform of sine 4t is. I said we know that, really, I hope you know that one. If you don't know the Laplace transform of sine 4t, better go back to the first lecture, okay, part 1, Laplace transform part 1, you'll have that all. Now Laplace transform of sine 4t, I hope somebody is speaking while watching this one because they know it. Okay, fine. It is 4 by s square plus 16. If it is cos 4t, then it will be s by s square plus 16. Okay, very nice. Now we know what is the Laplace transform of sine 4t. Now then, by using this first shifting theorem or first shifting property, Laplace transform of that same sine 4t when comes with e to the power of 3t, for example, it's a product. If it is a sum, for example, plus, then we'll separate it by linearity property, L of e power 3t plus L of sine 4t, but it is not plus, it is a product here. Then when it's a product, it should be compared with this one. This f of t is this sine 4t. It is appearing in both the situations. The extra function which is appearing is e to the power of at. Then this a is to be separated from that s. That same function f of s is now used, but s as s minus a. Now coming to the point, we know the transform of this one. This I call it as f of s. I hope you know what is f of k now, that before by k square plus 16, whatever variable is there, that a variable has to come. So if you compare with this one, that a value is 3. So I need to write it as f of s minus 3. Then as I said just now, if it is k, k will appear. If it is s minus 3 will appear. So 4 by s minus 3 whole square plus 16. So this is nothing but equal to the Laplace transform of this one. If you know about it, if you know about this function's Laplace transform, then that same transform can be used by slight modification to bring out the Laplace transform of this product where the other function is exponential. This rule to be applied only for exponential. If I have t square or t cube, I cannot apply this rule. There is a different procedure for that. There is a different property for that one. I hope you understood. Now I tell what is L of t square. That L of t square, you know that it is 2 by s cube. Now if I say it is multiplied with e to the power of 4t, then what comes? Then this same thing to be, I can't write just directly L of this one is equal to 2 by s cube. I am agreeing that I will change s to s minus 4. If you don't write this one, it will be meaningless step or wrong step. Okay, now here I am agreeing that I will change. So if this is not there, I will write only this much. Okay, So for L of t square it is this. When e to the power of 4t appears, I have to agree that I will change. This is an agreement. Okay, I am making an agreement that yes, I am going to change s as s minus 4. Now here is the agreement done. Now we are following the agreement. We are doing the change now. That is s minus 4 whole cube. I hope you will be able to tell the Laplace transform for a product of two functions if one among them is an exponential. So let's have one more, L of root t. I hope you remember L of root t is nothing but L of t power half. L of t power n is gamma of n plus 1 by s power n plus 1. So it is gamma of half plus 1 by s to the power of half plus 1, that is 3 by 2. Now L of root t is this one. Let me write it. Gamma of half plus 1. Gamma of half plus 1 is, okay, yeah, fine, L of t to the power of half. So gamma of n plus 1 by s to the power of n plus 1, that is gamma of 3 by 2 by s root s. Okay, now this is L of root t. I hope you are clear about this, right? Now when we are ready with L of root t, what will be L of e to the power of t into root t? That is equal to whatever transform is there for this root t. First of all, write the transform, that is gamma of 3 by 2. Gamma of 3 by 2 is nothing but equal to 1 by 2 into gamma of 1 by 2. I hope you know about the gamma function. Already I have recorded a lecture on gamma function, you can visit that. Okay, s root s, and gamma of half is root pi, so it will be 1 by, okay, I will write it just root pi here, and it will be 2 into s root s. So that same function root pi by 2s root s, I need to now change s as s minus 1, because here it is a value 1. So this is going to become root pi by 2 into s minus 1 into root of s minus 1. This is the Laplace transform for L, okay, e to the power of t into root t. I hope you got the point. To save space, I have written here, not following the systematic procedure. If I rub it, it takes some time. To save time, I have just managed this space. I hope you understood this one. Now the next part is about the proof of Laplace, proof of first shifting theorem.